Okay, so in this section, we're going to talk about units, and the reason I'm going through this is because I looked at Appendix B of the textbook, and I thought that although the textbook went through the kind of basics of how we need to keep track of different units on physical quantities, it kind of missed the incredibly rich structure that it already gives us to try to understand what's going on in all kinds of different situations. So this is going to be a very, I hope, easy introduction to the topic, and we'll see by the end of the chapter just how powerful only thinking about units can really be, right? All throughout this class, we're going to be talking about the idea that physical quantities have dimensions, and those dimensions are associated with units. This sounds super boring, and if you've seen this idea before, it's usually in the context of just making sure you've written your answers in whatever units the teacher wanted, right? Like maybe you are better at thinking in feet and pounds, and the teacher wants you to list all of your answers in meters and kilograms, right? And so this is like brushing your teeth and eating your vegetables and all of this stuff. And I think that's a real shame, because dimensional analysis is an incredibly powerful way to organize and classify not only physical numbers, but the abstractions that those numbers represent, right? So it's not just about checking your work or communicating to people who are used to different systems of units. It helps you remember what's going on in formulas. It can help you estimate the characteristic sizes of things, and it can even let you kind of act as a sort of shortcut to guessing the physical laws that are underpinning the world, right? So section 1.2 here, where I talk about units, is going to seem, I hope, very straightforward, very simple, and then we will quickly build it up into this really powerful structure. Okay. So great. So section 1.2.1 says that physical quantities have dimensions. Physical quantities have dimensions. And what is a dimension, right? Dimensions are some kind of abstraction that tells us the sort of thing a quantity is. So a physical quantity typically has a number associated with it, and it has a unit that refers to a type of dimension, right? And we all know this. When you ask me, how tall am I don't just say 5, because a pure number doesn't have a meaning that corresponds to a physical quantity, right? I have to say 5 in units of whatever. So I'd have to say I'm 5 feet tall, or I'm 6 feet tall, or I'm 3 meters tall, or I'm 18 cubits tall. None of those refer to the same height, of course, and they're all from different systems of units, right? And one of the points that we have to remember is that any particular dimension can be measured by any number of different units. The choice of units that we work with is basically completely arbitrary, right? And we agree on systems of units just so that it's easier to communicate with each other, right? So great. So in this set of notes, and also in this class, we're going to use different notations. And in the written text, this should be a lot clearer. For my handwriting, it might be a little bit ambiguous what I'm talking about. I'm going to use kind of what's called blackboard bold symbols to refer to dimensions, right? And I will use kind of normal typeface letters to refer to the units that go along with them. And some simple examples, I think, should make things pretty clear. So for instance, what about the idea of length or distance, right? Length or distance, right? The kind of thing that a height is, or the distance that you ran today, or whatever. So length, this has dimensions, definitionally, of length, right? It's one of the pure dimensions. And I'm going to write that with this kind of reinforced L sort of symbol. And it has units. It has units like, meters or feet or whatever, right? Starting out nice and simple. Mass is another kind of very simple, non-composite dimensional quantity. How much mass does an object have? This has dimensions that will denote with like one of these funny letter M's. And it has units like kilograms or grams or whatever. But for the most part in this class, we'll stick with SI units. Okay? So again, it's a dimension that is just its own thing, right? Okay, let's keep going. Time. Time is another incredibly important kind of pure dimension. So we'll say that it has dimensions of time, and maybe that looks a little too close to the letter pi, so I'll just make these a little bit closer. Dimensions of kind of bold script t, and it has units like seconds. like seconds. Easy peasy, right? Let's get to our first kind of composite dimensional quantity that we'll talk about in this class, speed or velocity, right? So speed, how fast something goes, is a measure of how far something goes in a particular amount of time, right? And so it combines some of these previous types of dimensions, right? So this has dimensions that are given by length times the inverse of time, right? And if you're more comfortable, you could also write that as length divided by time, right? So, or this. And it has units, miles per hour, or in SI units, meters per second. So you could write that as meters divided by seconds. You could write the same thing as, meters times seconds to the -1. It's -1 power means we're just dividing by it, so on and so forth. Okay, a little bit more complicated, but still I think pretty easy, pretty intuitive to understand. Another very important thing we'll see over and over in this class is the idea of acceleration. Accelerations tell you how rapidly the velocity of something is changing, right? So if you're accelerating really fast, you're rapidly changing what your velocity is. So it's a rate of change of velocity over time. So this means that it has dimensions of length divided by time squared. So I'll write that as length times time to the -2 again, or length over t squared. Okay, and it has units of meters per second squared. That's how we'll pronounce this combination. And you could also equivalently write this, if you're more comfortable with just expressing things like division, meters divided by seconds squared. Okay, there's just two more that we'll use over and over again that I just want to kind of go through so that we've made sure we've seen them. We just had acceleration. What about force, right? So in the physical world, forces are being exerted on objects all the time, right? And so force is another composite dimension. Dimensions. Maybe you know Newton's laws of motion, and if you don't, we will meet them again just in the next chapter. That tells you that forces are like masses times accelerations. And so that kind of gives you a clue that the dimensions here are going to be a combination of acceleration plus or multiplied by a mass. So this is going to have dimensions of mass times length divided by seconds squared. So mass times length times time to the -2, or kilograms meters per second squared. Right? And this combination, forces are so important that we have a name for this particular unit. So I should have written units of. And this combination is so common that we call the whole thing a Newton. So 1 Newton, or 1 N, is equal to 1 kilogram meter per second squared. Okay, and then of course there's energy. So we've got our preliminary list of kind of very typical physical quantities, the dimensions and the units that are associated with them. The last one on this list is energy. Okay, and energies are like forces over some distance, right? So for instance, if you imagine applying a force on an object in order to lift it up a certain amount, you've done a certain amount of work, and you've converted the energy in your muscles into a gravitational potential energy, as we'll discuss much more later on in this class. But so energy has dimensions of mass times length squared divided by time squared, right? So this has units of kilograms meters squared per second squared. So meters squared, seconds to the -2. And this is also such a common combination of things that we have a name for this combination of stuff, a joule, where 1 joule is equal to 1 kilogram meter squared per second squared. Okay. So I basically assume that you've all seen these types of definitions, if not these specific definitions before, and you kind of already know that, physical quantities, yes, they have these dimensions. When we want to talk about them, we choose a system of units, and then we describe a particular quantity as a number and a particular unit, right? So, what do you do if you want to change back and forth between different units, because different sets of units are kind of just arbitrary? You basically just multiply by 1 repeatedly until you get the right answer. But you multiply by 1 in a sufficiently clever way. So for instance, you might know that 1 meter is basically 3.28 feet, right? A meter is like 39 something inches, right? And we can rewrite this by dividing through. So if I divide through both sides by 1 meter, what I have is that on the left, I just have a pure number again. I'm dividing both a number and the same type of unit. So this is just the pure number 1. And over here, I have some expression, 3.28 feet per meter, right? And you probably know that when you're writing down a mathematical expression, you can take any number and multiply it by 1, and it's the same number. So for instance, if I tell you that, maybe I'm 2.5 meters tall, so if I say I'm 2.5 meters tall, you can say, oh, well, that's equal to 2.5 meters times the number 1, right? And we can write the number 1 as 2.5 meters times this combination, 3.28 feet divided by 1 meter. And units, when they're multiplying a pure number, cancel out. So I cancel out these meters, and I discover that 2.5 meters, cancel out, and I discover that 2.5 meters is 2.5 times 3.28 feet, or about 8.2 feet. Obviously, I'm lying. I'm not over 8 feet tall. More's the pity. Okay, great. Similarly, if you need to convert multiple units at the same time, you just repeat this trick until you have arrived at your consideration, until you've arrived at whatever system of units you want. So another simple example, and this is the same one that appears in the lecture notes. Suppose I have some density that I'm interested in, and this Greek letter rho, stands for a density, and what is a density? Let me use these brackets around a quantity to mean what are the dimensions of the quantity inside the brackets. So for instance, if I had, I guess I just make myself some more space. So for example, suppose I have a speed given by some number v, and I want to know what are the dimensions of v. I'll write these little brackets, and we know from up above that the dimensions of a speed are a length per unit time, length per time. Great. So, okay, the dimensions of densities. Densities are like how much mass do you have within a volume of space, and a volume of space is like length to the power of 3, right? So for instance, this might be kilograms per meter cubed as a canonical example. Okay, so what if you need to convert multiple units at the same time? Like, what if I say I have something ridiculous, 50 stones of rocks in a cubic cubit, right? So a stone is a very old British unit of mass. A cubit is what used to be the distance between, I think, the pharaoh's elbow and the tip of his finger, back before things were standardized. And, nobody knows what any of these units really are. No one thinks in terms of these units anymore. So if I tell you something like this, it feels pretty meaningless. But we can write this out and apply our multiply by 1 trick as many times as we want. So we say, okay, I have a quantity, which is 50 stone, divided by 1 cubed, and I'm going to start multiplying by 1, right? So you can go ahead and look up that a stone is, 20 some odd pounds or something. It's actually 6.35 kilograms per stone, right? So 3.65 kilograms equals 1 stone, which means 1 equals 6.35 kilograms divided by 1 stone. And I can do the same thing to change over this set of units, and I can say, okay, well, a cubit used to be non-standardized, but we can look up a rough approximation. It's like 1.5 feet. or you might say 0.457 meters, and then cubed, so that all of the units that I'm using here all cancel out, right? So stone cancels with stone, and 3 versions of cubit cancels with the 3 versions of cubit here. You go ahead and you work that all out, multiplying stuff together, and this is like 3,322.2 kilograms per meter cubed. And that probably doesn't mean very much to you. It doesn't mean very much to me either. I looked this up. This is approximately the density of like various igneous rocks. So, stuff that emerges as a result of volcanic activity. Great. Yeah, and if you want a picture, here is the rock that I found that has a density closest to this value. It's called gabbro. Here's a small piece of gabbro. Here's a very big piece of gabbro.